Welcome back. We're now going to take a look at a test of independence. And so this is the next thing we're looking at in this module, in this chapter, module 12, chapter 12. And test of independence is testing to see if two variables are independent of each other, or are they dependent? Does one variable influence the other variable? And so you might say, hey, is age and food choice related? And so when I asked ChatGPT about this, please explain, in simple terms, what is a test of independence in statistics? That was the example they gave, right? Like, hey, are age and food preference, are they independent of each other? Or does your age help determine your food preference? So are people who are teenagers more likely to eat Cheetos, right, than people who are in their 50s? So maybe age and food preference would be dependent for that food choice. Or maybe they'd be independent, but you could test that. And another one might be like, is gender, so here, is gender independent of beer preference? Is gender independent of beer preference? Or beer preference is not independent, right? Is not independent of gender. So beer preference, that would be two negatives, not independent. So beer preference is dependent on gender. So your gender helps determine your beer preference, whether you like light, regular, or dark. And so to calculate a test of independence, you're going to set up the null or alternative hypothesis. And to do that, remember we have this right here. So I'm just going to copy this and bring it back down here for our reference. And I will put that, I guess that's where we always put it, pretty much. I'm going to leave it there. So you set up your null or and alternative hypothesis. The two categorical variables are independent is going to be your null hypothesis. And so if you think about that in relation to the null hypothesis, they are independent, right? Nothing changed, current state, no change, status quo. I'm wondering if I could apply that. To two categorical variables are independent. Is that equality, right? I don't know if it's equality. Maybe there's more for us to learn here. But I always like to try to think about how do I create my null and my alternative hypotheses in relation to these heuristics, these rules of thumb that we've already learned about creating your null and alternative hypotheses, right? So we'll see. Or maybe we just take this on face value that when we're doing a test of independence, the null hypothesis is that the categorical variables are independent. Maybe they're starting from the assumption that everything's independent. And that's an interesting assumption to make. So, but anyhow, you create your null and alternative hypotheses, and then you select a random sample and record the observed frequency for each cell of the contingency table. So contingency table, that's an interesting phrase, potentially look that one up. And then we compute the expected frequency for each cell. And so the expected frequency is going to be the row total and the column total divided by the sample size. And so that's going to be the expected frequency. And then after we've done those steps, we compute the test statistic. And so here is the test statistic. And notice, again, we have this F and E notation. But if we go to see where I have ChatGPT explain this, I'm just looking for the test statistic here. And I've got a mosquito bugging me. And I'd like to not have it bugging me, but didn't get it. And so here's how they describe the test statistics. So we could just look at the textbook's description here versus that description right there. And we'll just put that up there to kind of align with that, so we can kind of see that is related to that. So there's that the fourth step there, and then determine the rejection rule. And so they have these, rules. I like drawing the diagram like this, so we'll see that in a second. And then also calculate your degrees of freedom. And so its rows and columns are the R's and C's. So alpha is the significance level with R rows and C columns. There are R minus 1 times C minus 1 degrees of freedom. And so we just have to calculate all that. So here's our data and a problem that we could work. The example is a beer industry association. And a sample of 200 beer drinkers is taken. The sample result is summarized in the following table. And so here are the observed frequencies. And then to calculate the expected frequencies, we're going to use this formula here. So I could copy this and then bring this down here. And I could just make this really small and just put it like right there. as a reminder that this is how we calculate our expected frequencies. And it's going to be the row total and the column total multiplied by each other divided by the sample size. So to find out if this is the observed frequency, and mathematically I tried to wrap my head around that. Y is 132 times 90 divided by 200. So for male light, the observed is 51, right? So we take the column total and the row total. Here's the row total and here's the column total. We multiply the row total by the column total, and then we divide by the sample size 200. And you can see that being calculated right over here for light male. So light male, it's 132 times 90 divided by 200, right? And then you get 59.4, which is right there. And I tried to wrap my head around why this, the column total and the row total multiplied by each other divided by sample size, like why does that make sense that this becomes 59.4? Because when you add all those up, you get 132. And so I guess, just vaguely like in a foggy gossamer distance, I could see that this is some proportion, right? And so I could do a proportion like 51 out of 132, and I could do a proportion 51 out of 90. And I could also do a proportion 90 out of 200, and I could do a proportion 132 out of 200. So 90 out of 200 would give me light, and 132 out of 200 would give me male, proportion of males. And so 132 and 90, both of them out of 200, it looks like that's a larger proportion, and that gives me 59.4. And so somehow that all works out, that adds up to 132 and then 68, and these add up to 90 and 77. So there's something mathematically, if I was to dive into it further, where it's about proportions, and I could kind of see how that, like a gossamer, foggy kind of distance, I kind of get an inkling of a sense about how this mathematics works. It's not just random, like this is what you do, but it's really kind of about proportions here. Just as if I wanted to see what percentage of males like light beer, I'd say 51 out of 132. Or if I wanted, that would give me 51 divided by 132 would give me the percentage, the proportion of males that like light beer. And if I did 51 out of 90, that would give me, in relation to males and females, the proportion of males in relation to females. How many males out of the total light beer drinkers? Out of the total light beer drinkers, what percentage of them are males? That would give me that. So somehow that multiplication gives me that percentage. So here are the expected frequencies. There's the formula. We calculate all those. And our hypothesis, and again, we start with the hypothesis, the two categorical variables are independent. And I'm just going to copy this and see if there's room for this here. I don't think there is. But the two categorical variables are independent, and beer preference is independent of gender. So maybe when you do the test of independence, you're just doing, the null hypothesis is that they're independent, right? So the two variables are independent. The two categorical variables are independent. And these are categorical because you're choosing one of these categories and you're also in one of those categories, though maybe you're also choosing which category you're in. If so, good for you. Good on you, as they'd say in Australia. And then we have a rejection rule, so our alpha is 0.05, and our degrees of freedom, we've got 3 rows, and we have 2 columns, 1, 2 columns. So we have 3 minus 1 and 2 minus 1, we get 2 degrees of freedom. And this is a chi-square test. And so it's going to be a one-tail test. And because it's a one-tail test because we're squaring this. And when we square this, we just get a positive value. So we're just checking out there in the far right to see if our value is too large. So there's that. And then we create our chi-square test statistic. And to create this test statistic, if we go back and get the formula for our test statistic, and this time in this video, we're looking at the textbook way first, right? And so we're seeing that. So here's that test statistic. But we will also see here in just a moment the ChatGPT explanation for doing it. And I don't know, I'm just mixing it up. So here is that test statistic. And when we calculate that, we have our observed frequency. And so the observed frequency, 51, 39, 51, 39, right? 51, 39. So light male, light female, and then we have all those observed values. And then we have the expected values, which we calculated. and then we find the difference between those two, and then we square those differences. And then once those differences are squared, we divide by expected frequency. And so expected frequency, let me figure out what that is. Hang on one second. Never mind, it's totally obvious. It's right here. So here's EIJ, and here's EIJ again, and this is EIJ. So we take this and we divide it by 59.4 and we get that. We take this and we divide it by 30.6 and we get that. And I don't know, just to verify that, calculator, and talk to you later, calculator. And if we do 70.56 and we divide by 59.4, the EIJ 59.4, it's just plug and play, we get 1.19. So that's how you calculate that. And then you sum all those up, you get a you get a chi-square of 6.45. And so if we bring up our chi-square table, so let me bring that up. Maybe I already have it open, do I? I do, sweet. And we have 2 degrees of freedom, and we're operating at 5% in the right tail, so that's gonna be 5.991. And so when we draw our diagram, let me get that, and let me just make sure I'm still recording, which I am. When we draw our diagram, let me bring this down to the next slide and then bring this one back up. There we go. When we draw our diagram, let me bring this one over. There we go. We have 0.05 is our level of significance, and 5% of our data is going to be from here to the right, 95% of our data will be from here to the left. And our critical value of 2 degrees of freedom is 5.991, so that's right there, 5.991. And then our test statistic, which we just calculated, is 6.45, and so that's 6.45. And what's next? This mosquito. Mosquitoes, what's next? And then 6.45 at 2 degrees of freedom, we have 5.991 and 7.378. And so you can see those right here, 5.991 and 7.378. So 6.45 is going to be like right between 0.05 and 0.025. So I just put this between 0.05 and 0.025. But whether we use the critical value approach or the p-value approach, both of our figures here are greater than these, so we're in the reject area. So we're going to reject this null hypothesis. And our null hypothesis is that beer preferences are independent of gender. And so in rejecting that, we're saying that beer preference is not independent of gender. So beer preference is dependent on gender. Beer preference is dependent on gender. So we're testing whether or not 2 variables are independent of each other, whether it's age and food preference, or gender and beer preference. I'm not so sure this is a politically correct example anymore that's in the textbook. Like, that's kind of a loaded area anymore to do stuff around gender. So here we have the p-value approach as the textbook presents it, and you can see reject. And then here we have the critical value approach as the textbook presents it, and you can see again reject. And then here is, just a little, I don't know, this is a bar chart, they would call it in statistics, though in Excel you'd call it a column chart. And it's a side-by-side bar chart where you see the preference for males and females for light and regular and dark beer. And you can kind of see that if you're female, according to this data, there's a stronger preference for light beer. And if you're a male, there's a stronger preference for regular beer, and then behind that light beer, and then behind that dark beer. So here's how ChatGPT explained it, and I really like ChatGPT's explanations. So we're going to read through it because it's fun. To explain the Beer Industry Association example, let's go through the steps starting with observed and expected values and how to get from one to the other. Thank you, that sounds great. And so to get this explanation, I downloaded this PowerPoint presentation, or this presentation, downloaded it as a PowerPoint presentation. I uploaded that presentation to ChatGPT, and then I said, could you please explain for me how to solve the example Beer Industry Association example. In this example, we are testing whether beer preference is independent of gender using a chi-square test for independence. The observed frequencies are this. Total number of observations is 200. The null hypothesis is beer preference is independent of gender. And the alternative hypothesis is beer preference is not independent of gender. And calculate the expected frequencies. And so the expected frequencies are calculated under the assumption that the null hypothesis is true, meaning that beer preference and gender are independent, right? So that's good to know, right? The expected frequencies are calculated under the assumption that the null hypothesis is true. And so what that means is like that's the current state. And so I'm just going to go get this here. And so that's an assumption that's being made. And that was the piece that was missing for me. And like, how are they figuring out that that should be the null hypothesis, right? The two categorical variables are independent. So it's just the assumption. You're just starting with the assumption. I'll just put this up here and then move it over here. You're just starting with the assumption, we'll put that right there, that that the null hypothesis is true. That's the status quo. There's no change. It's the current state, right? That beer preference and gender are independent. That's the current state. So that's the assumption that allows us to make that the null hypothesis. That's what I was curious about in the beginning. So I'm going to highlight that because I think that's important. And I can't stop right there, so I'll just highlight all of that because to me that just means, hey, take a look at this, and this is important, and then I'll put a little bit of a border around it like that. So there we go, and then just bring that back over like so, voila. And now, you know, the formula for expected frequency for each cell in a contingency table is this. And so it's row total times column total. And to actually calculate this, it would probably be easier to have this. So I'm going to cut that out. And oops, that's not going to do it. And on a Mac, you press Command-Shift-4, and you could do a snip. And then I'm going to bring this over here, and I need to grab it. And so that is right here. And it snips it and puts it on your desktop. And so you can see that there's the screenshot, and it's that one there. So I'm just going to bring that and drop it right here. And then I'll make this smaller, and I'll just put this here, and then I'll put a little text right above it, and I'll put here, these are observed, and I'll select that, and then make this like, I don't know, 12 is good. And then this is the expected. And so maybe just for symmetry, I'll just bring this down here and whoop, 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 whoop. There we go. And make this expected. Oh, all right, there we go. So here are the expected values. And we could even like just bold these and just like kind of make them pop, so that we really don't overlook that. We're like, that's important. So there's your observed, there's your expected. And so you can see here now, like 132 times 90 divided by 200 gives you this value right here for the expected. Yeah, so all good. And compute chi-square and observed minus expected. So again, here it might be good to just bring this guy over, and we'll Control-C that. And this mosquito, oh, did I get it? I did not. They're so fast. All right, so now I can paste this here, and I could grab that whole handle. I think it will scale everything down, and we'll scale that one down like that. So there we go. All right, so there's our expected, and that got a little bit too much crunch. There we go, like that. And you can see here, oh, we need both observed and expected. So let me get rid of this, because you have to, and we'll bring both these guys and copy those, and then just bring them over and paste them. And for this one, we just need to make this one smaller. So let's make this one smaller. And it'll go to that one, and we'll make it to this one. And then they'll be the same size, and we'll bring it under expected. There we go, and let's bring this one over. And we'll bring this one over. That's pretty good. So now we could do observed minus expected, and we got sigma sigma up here, which the young kids are really liking that phrase. And but here we just have one sigma, and so we could kind of look at it and try to figure out what they're thinking. And so here we have 51 minus 59.4, and we square it and we divide by 59.4. And that gives us that, and then that, and then that. And then you get all these and you add them up. So that's the sigma sigma, is you have to get each one of these. And then once you have each one of those, you add them up. I don't know, because there's no addition in here. So I'm not sure why the textbook has sigma sigma, but there's your test statistic, 6.446. 6.45 is what we came up with. And same thing, right? Round up from here, it goes 6.45. So here's the last step, ChatGPT, and determine the critical value. And so here's our critical value, level of significance. Critical value is 5.991, and we had 5.991 as a critical value right here, and there's our test statistic. And then make the decision. Conclusion. And here's where they kind of give you the information. And it's amazing. It's amazing to me, absolutely amazing, that you could talk with a computer and you could put stuff in and you could upload an entire presentation, a PowerPoint presentation. You could say, show me how to solve this problem. And in real time, as if you have a tutor there, a really smart tutor, or a textbook being written for you in real time. It's like, here's the answer. It's amazing. So at the 0.05 level of significance, we reject the null hypothesis and conclude that beer preference is not independent of gender. So beer preference is dependent on gender. This means that beer preference is significantly associated with gender. So it doesn't really tell us what that level of association is. It just tells us that it is associated. So that, ladies and gentlemen, is a test of independence.